So we're in section 5 already. And honestly, we kind of have two options. I could push through all the notes and then give you Monday to work, or I can do half and half. Something tells me you'd be better off if I did half and half, because I feel like if I taught you everything today, you'd probably forget a lot of it over the weekend, and then doing the work on Monday would be difficult. So I think I'll kind of split it up half and half. Now, a lot of this notation, a lot of this definitions, we've already actually gone over, the terms. Like I did my best to try to tell you what things were called ahead of time. An integrated answer is sometimes known as antiderivative, anti-differentiation, or just integrated, integral. Like there's all sorts of different words, all mean the same thing. What we haven't gotten to yet is if you do integration without numbers, it's called an indefinite integral. And I know I mentioned that word the other day, but we didn't really talk about what it was. So you have this picture here. Well, it's basically 5 of the same graph, but the difference is that they're all different heights. Where the difficulty comes. So when you're doing derivatives, it's pretty straightforward because you're just finding how fast the rate of change of something is. And you get an actual specific answer. If you do integration, what you're actually trying to do is you're given the derivative and you're trying to say what it came from. I mean, that's what antiderivatives means. You're given the derivative and you're trying to figure out what it came from. The problem is, like what's displayed up on the board. Those 5 equations are all similar. They call them a family of functions. They're all similar. The difference is they all have a different plus or minus number at the end. So they're all kind of like transformations. Like one would be raised up 1, up 3, up 5, whatever. But they all have the exact same slopes in the exact same spots. So if you think of taking the derivative of all 5 of those, they would all have the same derivative. So the difficulty is if we're trying to say what equation this derivative came from, is that it could actually come from a lot of different equations. So right here, I know it's kind of buried in this notes here. That's what we end up working with. At the very end of that answer, you're going to have to write plus C. And that's because we don't know what the number at the very end would have been, because the derivative of a plain number at the end is 0. So it doesn't show up. Ryan. I'm keeping that in the background. We can just play that every time somebody's on the phone. And then let's hope the video doesn't get taken down for copyright trademark. So that plus C is called the constant of integration. And it may not seem like a big deal to you. It's just like some random plus C you write at the end of the answer. But we make a big deal out of it because the AP makes a big deal out of it. And they dedicate a lot of points to plus C. You'll see that when we get there, a lot of the free response questions on the AP test Even if you get the answer wrong and you write plus c at the end, you will get 1 point for writing plus c, because they want it known that that plus c is a big idea that you need to know. So if you're integrating an equation, it has to have plus c at the end because you don't technically know what it came from. Okay, so that's kind of why I have it highlighted up there. We are definitely not doing this by guess and check. I wanted to get to page 3. So you'll see on the left-hand side, there's 4 functions. They're labeled with the little f. On the right-hand side is 4 functions with the capital F. And what this is implying is that if we integrate the equation on the left, we should be able to figure out the answer on the right. Now, you guys don't know how to actually integrate yet, though. What could we do to figure these out properly?
Do the derivative, but like in reverse?
Yeah, well, not reverse, but yeah. So what we're going to do is go to the answers on the right, and if you take the derivative of the answer on the right, it should match up with the equation on the left. Because the left represents the derivative, the right, the one that it came from. So I figure we'll do like 1 from each section. I don't think we need to do all 4, because there's like, if I remember right, isn't there 4 separate blocks of these groups? Yeah, and I don't think we need to do that. So here's the thing I definitely lied about, but I did because I thought you needed to hear it, is I told you we were done with derivatives. And we're definitely not. So integration is 100% based on derivatives. So there's a reason we spent such a long time on derivatives. It's because the second half of calc is based off of derivatives. So that's the way it goes. Let's look at A. No, let's roll. We need somebody to roll. Does anybody want to roll, or should I roll to roll?
I've never rolled.
Have you really?
Yeah, I've never.
Oh, I was going to purposely pick on somebody I didn't have before. I didn't realize you never did.
I think you should give it to Teddy so I can blame him if Peggy thinks
No. Oh. Oh, Shridula. That's right. I was trying to get it off the top of my head. Okay. All right, there's a lot of skill involved in this. You spin it, and then the ball comes out, and you read it. It sounds simple, but what happens is that thing's kind of a piece of junk, and it shoots the ball out at you a lot of times.
I thought you got the dice.
They were supposed to come overnight.
You want me to bring dice? I don't know my car.
No, I ordered them. They were delivered to my house at 11 o'clock. You're leaving?
I'm good.
Oh, okay, good. Okay, what number do we have? 26 is Andy. Okay. If we look at A, which one on the left is it going to match up with, and how do you know that?
The second one,
Okay, how come?
I think the derivative of the right side.
Okay, perfect. And then the derivative of plus C was, what's the derivative of plus C? But you're correct.
Was it just 0?
0. Because C is always a plain number, constant, so that'd be 0. So A would go right there. Okay, very straightforward. Good start. And obviously they get a little bit harder as we go, so I wanted to kind of start easy. 14 is Caden. Tebow. Yeah. So, I don't know. Which one should we go with? Let's go with F. Let's go with F. We want to try to find out what it matches up with. How about off the top of your head? What's the derivative of natural log again?
It's 1 over x.
It is derivative of natural log of x is 1 over x.
Yeah, so it'd be 1 over 2x divided 6 times 6x.
Nice. So we're basically doing u prime over u. So what did you say, 6x over 2x cubed minus 6?
Yeah.
Okay, good. And then frequently, the annoying part is that it can reduce a lot of times, especially natural log ones, just the way they're set up. I definitely can tell that none of these answers on the left match up with that. So we have to figure out how it was reduced.
We can factor out a 2x.
No.
Or we'll take out 2x from each side. And then... Oh yeah, 2. My bad. So just take out a 2 from the 6x.
Is there a typo here?
There's a 6 on the bottom. So
Well, let me 6 for the top.
Well, it it would be 3x over x cubed minus 3.
I misspoke. It's 6x squared on the top.
Oh,
Yeah, that's what,
that's what you were trying to tell me.
yeah.
Yep, good call. So,
So it should be 3x squared.
oh, now I'm annoyed I missed that. I was just writing stuff down and not really checking it. Yeah, it's easy to do that. I mean, like, you guys have done enough of these by now to know that missing things is super easy. That's why calc is hard. The natural log ones are by far the most annoying to integrate because frequently this can be written differently. And so there's going to be a lot of natural log answers that are equivalent but look different. That's what you're going to run into a lot. Okay, let's do a trig one. Yeah, that direction. Marlene. J, K, L, or M?
I did J.
You did J already? Oh, wow. Overachiever. What'd you get?
The second one on the left.
Okay, so what's the derivative?
Like just to summarize that.
Wait, what?
I got the second one on the
Yeah, I heard that part. I heard you say it was that one. Okay, but why?
sine goes to cosine, and then the 3x plus 1 stays the same.
Okay.
And then I simplified the negative 18.
Into.
The 6 cosine.
Wait a minute. Why'd they reverse them? They're throwing me off here. We're not supposed to take the derivative of the right. That's cruel. You know what? It's really hard talking and doing stuff at the same time. You had the right idea. The reason I knew something was off is because you would need to take the negative 18 times the 3 when you're doing derivatives, and that doesn't. So if you'll notice on this section, the integral symbol is before the problem. That integral symbol, is telling you to integrate. And so these answers over on the left are the ones that you would get as the answer. I should have absolutely seen the plus C, and then that should have clued me in. So we're taking the derivative of the ones on the left to get the right-hand side. Cruel. Okay, so you had the right idea 100%. Let's just pick that second one and try to find its match on the right-hand side, which very well may be J, which is maybe what you did? I don't know. Okay, so derivative of 6 cosine 3x plus 1 would be 6 negative sine, same angle, times,
Times 3.
okay, times 3 because you're taking the derivative of the angle. So that's where the negative 18 comes from, sine 3x plus 1. This is annoying. I even went through these this morning and I didn't even notice little details like this. Nope. We don't want to go to that page yet. That's what we're saving for Monday. Yes. Now, the reason I did this in different order is because of those multiple choice ones help us understand how they're set up between derivative and integral. Second half of this section is where we actually go through how to integrate. One thing you're going to run into is that frequently you're going to want to rewrite equations to be able to integrate easier. So we've gone through properties already, right? How should I phrase this? When we did derivatives of a fraction, do you remember what we had to do? Like, let's look at the third one there. If we were doing the derivative of this, what did we have to do? Quotient rule, right? Otherwise, a different option we had was to,
Make it the negative fifth.
so, if I remember correctly, most of you guys brought this up as x negative 5 and multiplied it out. I hate that myself, but it doesn't matter what I like and don't like. Me personally, it just makes more sense to like divide it on each term, but it works out the same way. Is you rewrote this as x to the negative 3 plus 4x to the negative 4 plus 5x to the negative 5. Now, the reason this is going to work a lot nicer for us to be able to rewrite things as, I'm not even going to call this a polynomial, but rewrite things as individual terms is because our properties allow us to do this. And we can separate and treat everything individually, which will make it much easier. And you don't even have to write these, oh shoot. See, talking and writing is hard. I don't know how, I see every student in the hall like texting, talking, and walking at the same time. And I'm always jealous. It's going to make things much easier for us when we can separate them, and you're not going to have to actually write them separate later on. What's snow? I'm going to put this in red because it needs to be known that it's a warning. I brought up the quotient rule first for a reason. The difficult part of integration is a lot of the rules of derivatives don't apply to integration. There is no quotient rule or product rule for integration. This is 100% the biggest mistake I see students will make once we get there. Because you're so trained for doing quotient and product rule in derivatives that it's almost like it's kind of habit, but it doesn't work. There 100% is many integrals that can't be done by hand. There's many integrals that can't be done by hand. You won't be given any. I'll just tell you that right now. Like, that would be like the cruelest thing ever, is if I gave you some integrals that you can't actually do. The biggest difference between the two topics in calc. When you're doing derivatives, you can take the derivative of anything. On integration, it has to be set up perfect for you to be able to integrate, because there's only so many methods and ways we know how to integrate by hand. And integrating on the calculator or a computer, 100% is a real thing, but you won't be given any that don't work out. even if they feel difficult. You won't be given any that don't work out. So writing things as individual terms is going to be helpful, slash, on this top one, is there anything you guys could think you could do to rewrite to make this look simpler to start with? Pretend you were doing derivatives. Would you like to do the derivative of 1 over cosine squared? What would you prefer to take derivatives of? Yeah, cosine of the -2 would work. Honestly, I didn't even think of that one. On trig functions, the reciprocals. So you don't have to write it as -2. You can write it as secant squared. But cosine to the -2 would work. I mean, we would write this as secant squared. The reason this one is going to be nicer is, do you remember what secant squared is the derivative of?
Tangent.
Tangent. So our goal is to be able to write integrals as common derivatives that we have found. So if you can write them that way, we would want to. This next one is kind of iffy because you will learn other ways to integrate this later on. But otherwise, this is when we first started doing derivatives, we did the same thing. We actually FOILed this out to make it individual terms. And we're going to do the same thing to start integration. So 9x squared minus 6x plus 1. You're frequently just going to rewrite things so it's easier for you to work with. That's basically all this is. This bottom one is probably the worst one. Can anybody think of how we can rewrite it simpler? So that they're all individual terms? Let's roll somebody. This is a cruel one to roll. Other way. Well, this is cruel to call on somebody for this, but we're going to do it. Literally the only desk that we don't have somebody. Oh, wait. No, those are open too, aren't they? 1? Wow. Oh, my gosh. Okay, you have a talent. 13 sounds like they're here. That's renowned. I can give you some guidance if you want to.
Yeah.
Okay. What did we do previously to this when we had the parentheses squared?
Change it.
Foiled it out.
Oh, yeah.
I mean, like you were talking derivatives, that's fine. Okay, so I'm going to start by foiling out the top. So that would become x squared minus 6x plus 9. Currently it is divided by square root of x. The problem above this one, what did we do when we had a denominator that was a single term?
We subtracted.
We subtracted the power,
Yeah.
correct? Or you could bring it to the top as a x to the negative half power and multiply it out. However you want to phrase that. Do you think you could give me the answers to write in here?
Yeah, so.
Okay.
The x to the power 1.5.
True, 3 halves though.
And then x to the power half.
Perfect.
That is 6x to the half. And then 9x to the half.
Negative half. Very close. Nice job. Nice job. That's pretty tough to do, on the spot, just trying to read it off for everybody. There isn't anything technically wrong with using decimal powers, but you're going to want to use fractions, and you'll find out why. Okay. I think I'm going to stop there because, like I said, if I just shove through this, I think you'll forget it all over the weekend. And I don't know if you guys are I don't know if it's true or not, but I feel like there's going to be a lot of prom planning things this weekend, which means you guys are going to lose time, but I could be wrong.
Oh, right, our prom comes up pretty.
It's next weekend, yeah.
I don't know why ours is so early.
Thank you. Didn't get to roll nearly as much as I thought. Though.